You've studied before that some functions can be broken down into infinite series. For example, let's think of a geometric series where r is the common ratio and the first term is 1. You've also learned that this infinite sum converges to a1 over 1 minus r if r absolute value is smaller than 1. This means that r is between 1 and minus 1. Let's change the notation, replace r with x, and since our first term is 1, we get this sum. The infinite series of x to the power of n equals 1 over 1 minus x. And this is always true for if x absolute value is smaller than 1. This means we can express the function 1 over 1 minus x as an infinite series on the minus 1, 1 interval. Let's have a look at the partial sums and also see the graphs. Let's see, the second partial sum is 1 plus x as we have 2 terms. The third partial sum has 3 terms. The next will have 4 terms and so on. We will see it only until the sixth partial sum. Now let's have a look at the graphs. First we will graph the function itself, which is 1 over 1 minus x. Then we will highlight the interval we're looking at, which will be between minus 1 and 1. And now we're going to graph all the partial sums one by one. Let's see the second partial sum. Then let's see the third partial sum. It has a bit better fit. Then the fourth has even better. This is the fifth. And this is the sixth. As you see, it has an even better fit than the previous one had. As we increase the number of terms in the partial sum, we will always get a much better fit than the previous one. Now this was a good example for a power series. Now let's see what a power series is. An infinite series of the form infinite sum of an times x to the power of n, which is equal to a0 plus a1 times x plus a2 times x squared plus a3 times x cubed and so on, where x and n can take any values for n, which could be 0, 1, 2, 3 and so on, is called power series in x. Let's have a look at our first example. Use infinite sum of x to the power of n to find the power series representation of gx. Indicate the interval on which the series converges. Use graphing calculator to graph gx and the sixth partial sum of its power series. Here we have 3 tasks to complete. First, we need to find the power series representation for gx. Then we need to find the interval on where this power series converges to gx. And finally, we need to graph gx itself and the sixth partial sum of the power series we found. I will use GeoGebra, but feel free to use any other graphing options, a graphing calculator or Desmos, whichever you prefer. Since our task is to use infinite sum of x to the power of n, it means that we will use the outfit, the form of fx, which is 1 over 1 minus x. Now this means that we need to see gx in the form of 1 over 1 minus something. For this something, I will use a different variable. Let's call it u. And our job is very simple. We simply need to solve this equation for u. We take the reciprocal, then we will subtract 1, and finally we take the additive inverse of all terms. So u equals x minus 2. Now what does it mean to us? Well, it means that gx equals to fx minus 2. Therefore, here, imagine to write in x minus 2, and if you simplify, we will end up with gx exactly. That means that instead of x, we need to substitute x minus 2. So therefore, on the next slide I will summarize. Here, instead of x, I will use x minus 2, and also here, instead of x, I will use x minus 2. This means that the power series for 1 over 3 minus x function is infinite sum x minus 2 to the power of n, and the interval is x minus 2 absolute value is smaller than 1. In order to find the interval where it converges to gx, we need to solve this inequality for x. I'm going to write it down, and since this is an absolute value inequality where the absolute value is smaller than a number, it means we can rewrite it as a compound inequality. This means x minus 2 is between -1 and +1. Now we need to add 2 to each side, so we will see that x is between +1 and +3. This means to us that when we graph the function and the sixth partial series, we will focus on this interval to observe how the two graphs fit. Well, the sixth partial sum has 6 terms, therefore we can write it as sum of x minus 2 to the power of n, where n goes from 0 to 5. Or we can also write out all the 6 terms. 1 plus x minus 2 plus x minus 2 squared plus x minus 2 cubed plus x minus 2 to the power of 4 plus x minus 2 to the power of 5. And now let's see the graph of 1 over 3 minus x and this sixth partial sum. Here we go. I highlighted the interval of the convergence, which is between 1 and 3. And as you see, between these two values, we see a very good fit. But if I'm looking out of this interval, I notice that the two graphs will not converge anymore. Now it is your time to practice. The task is very similar. You have 2 different functions, and the task is to write the power series representation using sum of x to the power of n. And again, you need to find the interval on which this series converges to the functions. And finally, you need to use graphing calculator or GeoGebra or Desmos to graph the function and the sixth partial sum. And now let's see the answers. We use fx as a template, so we can find u easily. Here is our power series. The interval of convergence, again, we will use u. So therefore, we will get this compound inequality. The sixth partial sum is this. We use ends only between 0 and 5. And here is our graph. The green is gx and the red is the sixth partial sum. And now in the second part, again we use this as a template. We need to divide both levels of this fraction by 2. So we get 1 on the top, similarly to the right hand side. And from now on, it is easy to express for you. We get this as our power series. We can find the interval of convergence easily. Again, we use this compound inequality, and we get -3 to +1. And here is the sixth partial sum. Again, n goes from 0 to 5. And here we go. Green is again hx, and red is again the sixth partial sum. I hope you've got both of them correct. The power series representing e to the power of x is called the exponential series, and it's given by infinite sum of x to the power of n over n factorial, which converges for all x. Well, this means that we can use this formula for any x values and not only for a small interval. Also, I would like to show you how do we receive the first two terms. I think starting from the third term, it's very clear, but the first two terms need a little bit more explanation. Well, the first term comes from n equals 0. Let's substitute 0 into this formula. X to the power of 0 gives us 1, and 0 factorial is also 1 by definition. So 1 over 1 equals 1. Now let's see if we use n equals 1, that will give us the second term. X to the power of 1 is x. 1 factorial is 1. X over 1 gives us x simply. So this was the explanation of the first two terms. X to the power of 2 over 2 factorial is simply substitution into the formula. Example 2. Use the fifth partial sum to approximate the value of e to the power of 1.5. Round to 3 decimal places. We know that e to the power of x converges to the exponential series in all x. Therefore, a partial sum will give us an estimation for the value of e to the power of x. The task is to use the fifth partial sum. This means that we include the first 5 terms of the series. This will be only an approximation. And this means also that we only use n from 0 to 4. Once we have this, we can simply substitute our x value, which is 1.5 this time, and type it into our calculator. Here we go. Don't forget to round to 3 decimal places. Now it is your turn to find an approximation using the fifth partial sum of the exponential series. Please pause the video and press play once you have your answer. Here are the answers. I hope you've got all of them correct.